Now, this table, we're going to spend time here, okay? And by the time we're done, you'll get a firm understanding as to what's happening with this entire graph. And so therefore, any questions that's posed at you, you'll sit back, relax, take a deep breath, and you'll approach it, and you will conquer this. Let's take a look at the table. The x-axis represents only, pay attention, only represents the proximal convoluted tubule. Only. It's not the distal convoluted tubule, and sure as heck isn't your DCT. Only the PCT. That's the entire length here. 100% on the x-axis represents a percentage of how much you've traveled through, what segment of the nephron? PCT. Stop. What's on the y-axis? This is going to be a ratio. You love ratios now? I hope so, because ratios mean what to you? Concepts. Your goal in medicine is to strive for concepts. Period. The more concepts you put into your head, the more that you're able to truly understand medicine. And no matter what kind of question is thrown at you, you'll think about it, but then eventually you immediately go to your foundation and you eventually come up with the right answer. Or at least you'll be in the right vicinity, right? At least you're not barking up the wrong tree. So the concept of ratio on the y-axis is the following. Dissect the following. Tubular fluid. What does that mean to you? Urine. Plasma is a denominator. Where are you? Blood. Okay, let me ask you something. If your numerator increases, what happens to your ratio? Increases. Okay, I can't help you if you got that wrong just now. So if your numerator increases, the ratio increases, right? Okay, now, if you're going to increase your tubular fluid, then what have you done? Is that secretion or reabsorption? Pay attention. Get this right. Secretion, more importantly. Isn't that secretion? Yes. What if you increase the denominator? What happens to your ratio? It decreases, right? What does it mean medically to increase the plasma level of a substance? That's reabsorption. How can you prove this, Dr. Raj? With this graph, I want you to pay attention to 1.0. You see it? 1.0 is the middle ground. So now, if you go below 1.0, which means the ratio is decreasing, what component or parameter of this ratio are you increasing? The plasma. What's that mean to you? Reabsorption. How can I prove this to you? Take a look at these substances on this graph. Specifically, glucose, find it. Amino acids, bicarb. At least pay attention to those three. Those three, as you travel through the PCT on the x-axis, what are its features? Reabsorption, 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 right? Remember, once again, are you supposed to normally find glucose in your urine? No. Why? Almost 100%, if not 100%, gets reabsorbed, right? What does reabsorption mean to you? Increase my plasma. Increase my plasma, because it's being reabsorbed. There you have it. So by the time you get to the end of the PCT, the x-axis, look how much glucose you have, please. Zip. Your tubular fluid to plasma ratio is decreased like crazy for glucose. So anything below 1.0, you're increasing the concentration of that substance into my plasma, hence reabsorption. Now, does that mean that anything at 1.0 means not reabsorption? Listen, I want you to take a look at sodium. That sodium right there is that dashed line, and it's right around 1.0. So what does 1.0 mean? It means isotonic. It means that you are exactly where the osmolarity should be with the tubular fluid and plasma, and it's at an equal ratio of 1.0. Do you see where sodium is? Sodium is almost exactly at 1.0 from the beginning of your PCT until the end of the PCT. Let me stop there for 1 second. If you were to tell me, based on this, that sodium is not being reabsorbed in the proximal convoluted tubule, does that make any physiologic sense to you? No. Because you know that sodium in the PCT, 2/3 of it is reabsorbed where? 66% of your sodium is reabsorbed in the PCT. So what does this close to this flat line or 1.0 mean to you? It means that you are reabsorbing sodium in the PCT. Do you remember in the previous discussion just now that I told you that in the PCT, the reabsorption is in what form? Isotonic. Isotonic. What does that mean to you? A plasma osmolarity of approximately 300. That means that not only are you reabsorbing sodium, but then also water in an isotonic fashion from the beginning of the PCT until the end, and thus you'll find sodium to be almost exactly at 1.0. You need to interpret sodium as such. Now, things that are important for us, I want you to move up to the green lines here. The green lines indicate creatinine and inulin. I want you to focus on inulin first. Okay? On inulin, now you tell me, close your eyes, and tell me about the characteristics of inulin. Filtered, yes or no? Yes. Inulin, PCT, reabsorbed, yes or no? No. Inulin, PCT, secreted, yes or no? No. No modification of inulin in your PCT, period. What gets filtered gets excreted, correct? So therefore, filtered load equals excretion rate. In other words, clearance equals GFR. You understand that from physio? We're good to go. Now we can move on with our discussion of inulin. We're not done yet. Because now you're thinking to yourself, Dr. Raj, I see that inulin. I understand what you're saying from before. I get all about inulin, but I'm not quite sure why by the time I start from the beginning of my PCT with inulin, and I get to the end of the PCT, and I find an inulin is 3.0. This is why. So you know there's no modification of inulin. It remains firmly steadfast in your PCT, period. There it is. It's never going to move. No modification in the PCT. Inulin remains. Tell me about water. Tell me about water in the PCT. 2/3 of your water is reabsorbed from the PCT. So what happens to the concentration relatively to inulin? If all that you're doing is reabsorbing water, what's left back in the PCT? The solute, which is inulin. If you absorb your 2/3 of your water, how much do you increase your inulin relatively? 3 times. Hence, by the time you get to the end of the PCT, you've increased your inulin to a level of 3.0. Once you understand that math, we can move on. But you want that to be digested first before we move on. What does this graph represent? Inside the PCT. The more that you reabsorb your water, the more that you have inulin left in your PCT, moved up to 3.0. So tell me about inulin. That is the perfect measure of GFR on this graph, isn't it? Isn't it? Clearance equals GFR. Okay, let's move on to creatinine. How important is that? You know that it's constantly being broken down by muscle. It's being filtered, correct? Yes. Is it being reabsorbed? Not at all. Is it secreted? Yes. How much? Slightly. So therefore, if you find that your tubular fluid to plasma ratio, in which you find your line to be counterclockwise, what that means is to the left of inulin, then you know secretion has taken place. And you know that already about creatinine. And you should find a little bit more of your substance inside my urine compared to that what you find at the beginning of the PCT because it gets slightly secreted. Now, what is a substance that you know that is at low levels purely secreted from the PCT? Welcome to PAH, para-aminohippuric acid hippurate, right? And you know that PAH, you tell me, is going to measure what parameter? Renal plasma flow at low levels. We've discussed that like crazy. You understand at least what I've told you here in terms of the graph for physio. Then in pathology, the different things that are going to go on would make perfect sense, and they can't shake you. At least lay down this foundation for me before moving on. Now, the only thing that I wish to bring to your attention is a little bit more detail here, because these are the type of questions that you'll get. Take a look at chloride. At first, it looks like it's increasing, but no. Chloride here, well, once again, at first, water is being reabsorbed. So relatively, what's happening to chloride concentration? It's increasing. Then it hits a flat line. What's that flat line mean to you? It's still being reabsorbed, but how? Isotonically. Read the stanza. That's exactly what we're saying. Chloride reabsorption is a little bit slower. Thus, you find an initial increase because water is being reabsorbed faster. Or should I say, chloride is being reabsorbed slower than isotonic. What about sodium reabsorption? We already said that it was isotonic in nature, so it nearly matches that 1.0. Okay, now overall, things that we've talked about a few times, and actually multiple times here. We have renal plasma flow of 600. Here it comes to the afferent arteriole. We're going to go through this quickly. We've done this plenty. 600 milliliters per minute of renal plasma flow coming through the afferent arteriole. Of that, what's filtration fraction? You tell me. Good, 20%. That means that 120 is being filtered. How much is left over in my efferent arteriole? 480. Next, what are you going to do? What kind of substance might you want to use so that you can measure all of your renal plasma flow? Low dose para-amino hyperate. Everything gets secreted, and you're going to find renal plasma flow. So net effect, what kind of things that we're looking for? We already talked about reabsorption, and we talked about secretion. I need to put in something else. You ready? What is it that allows for filtration to take place? Listen to my question. What is it allows filtration to take place? Where is that? Up in the glomerulus. It's hydrostatic pressure. What's hydrostatic? Pushing, pushing, pushing. What letter do we use medically to designate hydrostatic pressure? PPP. Use it to your advantage because that is your pushing pressure, right? Hydrostatic. And it's quite high when you are traveling to the afferent arteriole and filtration will take place. In the meantime, what other stalling force do you have in your plasma? I believe it's called oncotic pressure, right? And that's your protein. Should albumin ever pass through your endothelial cells? Never. It should never pass through the glomerulus. So therefore, as you go from the afferent to the efferent arteriole, what then remains behind in your plasma? Your albumin. What then happens to oncotic pressure? Increases, right? Oncotic pressure physiologically should increase as you go from the afferent to efferent arteriole. By the time you get down to the peritubular capillary, look where you are now. By the time you get down the peritubular capillary, your oncotic pressure is increased. That makes perfect sense. Why? Tell me about water. 2/3 of your water is reabsorbed. So therefore, aren't you pulling the water out? Who's going to contribute to that? The oncotic pressure. Who is that? Albumin. The albumin that never should have physiologically normally filtered through.